let's get started. Last day before you get to go back, right? Yep. You're over the moon? Yeah. Okay. So starting with discrete math kits. Review from last time, although you geometry kids have seen all this too. Review from last time, last week. What was the section about that we did?
Relations.
Relations. Tell me, what is a relation?
It's a set of ordered pairs.
A set of ordered pairs. That's now how we're going to encode a relation. So a relation, just some set of ordered pairs. And we talked about 5 different properties that a relation could have. First of all, it could be reflexive. Tell me in high-level language what it means for a relation to be reflexive.
Everything is related to itself.
Everything's related to itself. So you geometry kids, one of your first axioms of congruence is that congruence is going to be reflexive. Everything is congruent to itself. So a relation, like congruence, is reflexive if for all x in whatever set you're talking about, it's always related to itself. Next one was symmetric. In high-level language, what's symmetric?
If x is related to y, y is related to x.
Yeah, if x is related to y, then y is related to x. Again, if our relation was congruence, that would say if x is congruent to y, then y is congruent to x. Since congruence is symmetric. Next one, transitive. What did it mean to be transitive?
If x is related to y and y is related to z, then x is related to z.
Perfect. For all x, y, z in whatever set we're talking about. Notice that that's an implication, so we read implications as if. If x is related to y and y is related to z, then x is related to z. And then we had irreflexive. What did that one mean in high-level language?
Nothing is related to itself.
Yeah, nothing's ever related to itself. So for all x in A, x is not related to x. I'll put a line through it to mean the not. And then the strangest one, anti-symmetric. What did that one mean?
If two things are related to each other, then they're the same thing.
So for all x, y, and A, if x is related to y and y is related to x, then x equals y. The high-level way we say that is there's symmetry only if it's the same object. Anti-symmetric. You geometry kids, you won't see those bottom 2, but those top 3. Now those top 3 relations, they show up. They're so ubiquitous. They show up in all different fields of mathematics. For example, congruence. For example, when you're talking about similarity, when you get into geometry, it's going to have these 3 properties. Those of you who did topology, you might remember going all the way back to homeomorphisms. Oftentimes, whatever field of mathematics you're talking about, it has its associated relation that has these properties. So a relation that has these 3 properties we call an equivalence relation. Now I'm going to accidentally call a congruence relation 100 times, because for some reason I always do that. Call me out when I do that. It's called an equivalence relation. So let's go over its exact definition. Let R be a relation on some set A. A could be the set of all real numbers. A could be the set of all geometric figures. Just some set A. We call R an equivalence relation. I will now use E dot R dot to mean equivalence relation, so I don't have to write that 1,000 times. So we'll call R an equivalence relation, provided that it is reflexive, symmetric, and transitive. Those top 3 properties. Make sense?
Yep.
So in chapter 4 for you geometry kids, your first 3 set of postulates are going to essentially say congruence is an equivalence relation. And that's exactly what it's going to say. All right, some examples. The same height relation, we can think about that as being on the set of all people. Having the same height. Do I have the same height as myself?
Yes.
So it's reflexive. If I have the same height as you, do you have the same height as me?
Yep.
Yes. If I have the same height as Bob and Bob has the same height as Jim, do I have the same height as Jim?
Yes.
Yes. So it's an example of a congruence relation.
Equivalence.
An equivalence relation. Okay. Next one. Congruent. We already talked about that one in geometry. Every figure is congruent with itself. If figure X is congruent with figure Y, then figure Y is congruent with figure X. If X is congruent with Y and Y is congruent with Z, then X is congruent with Z. Same last name. There's another one. Same last name. Do I have the same last name as myself?
Yes.
If I have the same last name as you, do you have the same last name as me?
Yes.
If I have the same last name as Bob and Bob has the same last name as Jim, do I have the same last name as Jim?
Yes.
Yeah, so it satisfies those 3. So there's 3 examples of an equivalence relation. Okay. Now we're going to talk about a particular equivalence relation that seems somewhat abstract, out of the blue. When do we ever actually use this? It's actually quite a useful relationship that, for us discrete math kids, it will keep coming back as we go throughout the book. It turns out it's very important in number theory. If we ever get where I want to get, which is like Our last class would be about RSA encryption, learning how that computers actually encrypt things. This is very heavily tied into that. It's a very important concept to get at a very low level. So it's one that seems way out of the blue, but turns out to be extremely useful, and we use it all the time in our modern world. So let's go over what exactly it is. Teach me how to read this. Let
N in the integers.
N
Plus
in
positive integers.
the integers with a plus there. So let n in the positive integers, or let n be a positive integer. So whatever n is, it's something like 4, 7, 11, some positive integer. We say integers x and y are congruent modulo n. Congruent modulo n, provided that n divides their difference. If their difference is divisible by n, then they are congruent mod whatever that n is.
Okay.
Here's the notation we use. X is congruent to y mod n. That's how we read that. What exactly does that notation mean? What's it defined to mean? It's just a way of saying n divides x minus y. That's all it means. Okay, let's go over some examples, start getting some intuition for this. True or false? 13 is congruent to 7 mod 5. How do you check that? What's 13 minus 7? 13 minus 7 is? 6. Does 5 go into 6 evenly?
No.
Is 5 a factor of 6? No. If this were 8, now would it be true?
Yes.
What's 13 minus 8? 5. Does 5 go into 5 evenly? Yes, it goes into it exactly one time. Let's try another one. Is 96 congruent to 36 mod 6?
Yes.
How do you know?
96 minus 36.
What's 96 minus 36?
60.
60. Does 6 go into 60 evenly?
Yes.
Some integer number of times? Yes. All right, let's try another one. Is 0 congruent to 7 mod 2?
No.
What's 0 minus 7?
Negative.
Negative 7. Does 2 go into negative 7?
No.
No. What if it would have once again been an 8 here? Is 0 congruent to 8 mod 2?
Yeah.
What's 0 minus 8?
Negative 8.
Negative 8. So 2 doesn't go into negative 8, right?
No, it doesn't.
Of course it does. It goes into it negative 4 times.
Yeah.
Okay, so don't let the negatives throw you off. Perfectly fine numbers. All right, let's try another one. Is 7 congruent to 7 mod 9?
Yes.
What's 7 minus 7?
0.
0. Does 9 go into 0?
Yes.
Some integer number of times. Does it go into it evenly?
Yes.
Yeah. How many times does 9 go into 0?
0 times.
Exactly 0 times. That's an integer. So if it goes into it an integer number of times, it divides it.
Yeah.
Okay, let's try another one. Negative 19 and 13. Are those congruent to each other mod 8?
Negative.
Negative 19. That's a negative sign.
Yeah.
Can you see it?
Yes.
We got the first right answer. Yes.
By 4.
What's negative 19 minus 13?
Negative 32.
Negative 32. Does 8 go into negative 32?
Yeah, negative.
Yes, negative 4 times.
Sorry, I got something.
All right. Is negative 1 congruent to 1 mod 6?
No.
No. Negative 1 minus 1 is negative 2. Does 6 go into negative 2? No. So that one is not the case. All right, what about this? Does 1,927, is that congruent to negative 3,691 mod 2?
Yes.
Yes. How do you know?
Because when you subtract them, you get an even number.
Yeah, an odd minus an odd or plus an odd is always even. And so 2 is going to go into it an even number of times. However many times, I don't know. You don't need to know what it is to be able to come up with your answer. That it is. Right?
Yeah.
So the difference between two odd numbers is always an even. An odd plus an odd is always an even. Good?
Yeah.
And then what about this one? Negative 13. Is that congruent to,
No.
well, add the two together, you get 10.
You're minus 1.
Oh, you have to minus them. So negative 3 minus 13 is negative 16, and 5 does not go into that. Okay, there we go. There's some examples. This is one of those relations. I know when you first see it, it seems like the most useless relation on planet Earth. And so you just kind of have to take my word for it that it turns out this is extremely useful, and we'll see the use later. For now, we just got to get comfortable using the thing. Okay, so now let's do our first little theorem here. We're going to prove that congruence mod n is an equivalence relation. This relation here that we're talking about is one of these equivalence relations. It's one of these things that say that two things are somehow the same. That's what equivalence relations say. They're ways of saying two objects are in some sense the same. When you're saying two triangles are similar, you're saying that there's some structure that they both have that's the same. So, for this one, let's get started. Congruence mod n, first thing we need is some positive integer. Right? It only makes sense when you have a positive integer when we look at its definition. So let n be some positive integer. Let n in the positive integers. Okay. Now, we first, if we're going to prove that it's a congruence relation, an equivalence relation, what's the first thing we have to show?
That is reflexive.
That's reflexive. So I need to show that every number is congruent to itself mod n. Is it always and forever the case that x is congruent to x mod n? Is this true all the time no matter what?
Yeah, the difference is 0.
What's x minus x?
0.
0. Does n go into 0 an integer number of times?
Yes.
Yes, always 0 times. So it should always and forever be the case. So now let's do the proof of that. So let x be any integer. My job is to prove that x is congruent to x mod n. So let x be an integer and observe that n divides 0. Since n divides 0, n divides 0.
Yeah.
But that's exactly what we mean by the definition of this thing. What exactly does it mean to say x is congruent to y mod n? It means n divides their difference. So if n divides their difference, then those two things are congruent to each other mod n. So that's how we prove it's reflexive. Okay, now that's reflexive. What do we need to prove next?
Symmetric.
Symmetric. I need to show that if x is congruent to y mod n, then y is congruent to x mod n.
Is it the same then?
Yeah, the same n. We just pick some random n so that this relation is now defined.
Okay.
All right, so let's do symmetric. So let x and y be integers such that x is congruent to y mod n. Our job is to prove what we're trying to get.
Why?
I'm trying to get that y is congruent.
Y is congruent to x, so I somehow need to flip those two. So plugging in the definition, unraveling definitions, always the first thing you do, right?
Yeah.
You assume the antecedent, then you unravel your definition. Here's exactly what it means. N divides their difference. Now what does it mean for n to divide x minus y? It means n goes into it some integer number of times. What do we mean when we're saying something like 5 divides 30?
I mean, there's a number
5 goes
that
into 30, a number.
Some integer number of times. In that case, it's 6. So since I can find something such that 5 times that gives me 30, I can say 5 divides it. Right?
Yep.
So if n divides the difference, what do I know?
That n times something equals the
That there must exist some integer k, reading that notation, there exists k in the integers, such that n times k is equal to x minus y. Same thing we had over here. How do I know that 5 divides 30? 5 times something equals 30. How do I know that n divides x minus y? N times something equals x minus y. Now, multiply both sides by a negative number, or multiply both sides by negative 1. You with me?
Yeah.
And what happens when you take a difference, a minus b, and you multiply it by negative 1?
turns into a sum.
It doesn't turn into a sum, it's still a difference.
Oh, no. It's
Multiplying by negative 1
Switches their signs.
Swap.
swaps the order. So when you take negative 1 and you multiply it by a difference, negative 1 times a is
Negative a
minus a, negative 1 times negative b is
plus b.
plus b. Now swap the order, and so it's just b minus a. Good?
Yep.
So that's the way you always think about it. Multiply by negative 1 just swaps the order. So, same thing here. I'm going to multiply both sides by negative 1. I'm going to apply that negative with the k. I'm going to use that negative to swap my order. Follow the jump there?
Yep.
Alright. Next, that means n times some integer equals y minus x. So, n divides y minus x. And once again, if n divides y minus x, that's the exact definition of y is congruent to x mod n. Therefore, it's symmetric. And then I was about to do transitive, but I realized it's a homework problem. So I started out, but you guys will have to do this on your homework. So let x, y, and z now be integers, such that x is congruent to y mod n and y is congruent to z mod n. You're going to do the work to prove that x is then congruent to z mod n. This will give you two equations. You're going to have to substitute one into the other
Okay.
to eliminate your y. And then you'll get that it's transitive, therefore it's an equivalence relation. Any questions so far? Okay. So next, let R be an equivalence relation on some set A, and let little a be a member of big A. The equivalence class of A is the set of all the elements in big A related to little a. Writing that out in dense notation, here's how we're going to write an equivalence class on A. We're going to put brackets around it, and that is going to be the set of all x in big A, such that x is related to little a.
Okay.
So let's do an example. We'll say that A is everyone in this room. So this will be our set of objects that we're talking about. And we'll use R is the same last name relation. You with me?
Yep.
Yeah.
So now we got to pick someone out of this room, pick some little a to define their equivalence class. The little a we're going to pick is going to be me. All right, there I am. So who is the equivalence class on me? What's my equivalence class? It's going to be the set of all people with the same last name as me. What's my last name?
Tim.
Timpson. So whose last name is Timpson? We only got one. That didn't work out like it usually does. So Alex, and then I have the same last name as myself. And so we're the only two people with the same last name, or with the last name Timpson. And if I pick someone else here and I wrote whatever their equivalence class is, it's going to be the set of all people with their last name. So I pick some Hammond here, and we'd write the set of all Hammonds as an example. Right?
Yeah.
So what's an equivalence class? It's everyone related, it's all the objects related to some particular objects. What's my equivalence class? The equivalence class that I am in, it's everyone related to me under that relation. If we're using this has the same last name relation, that's the way it would work. If we instead did the same height relation, once again, that's an equivalence relation, reflexive, symmetric, transitive, right?
Yeah.
Dude, hey, out. I'm done. Out. 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 All right. Next one. Has the same last name. Go down to the office. Told my kick you out. Now, if we say it has the same height relation, this is everyone who has the same height as me. So, I'm 5'9", so who's everyone that's 5'9"? So it would be me, Alex again, and whatever her name is, sorry. Don't know your names. But that's everyone who would have the same height as me in that. So, what is an equivalence class given some object? It's everyone related to that object. If we were in geometry and you pick some triangle, and the relation we were talking about was congruent, then its equivalence class would be all the triangles congruent to it. Okay. Let's see. Next. So we're going to look now at the relation R, and it's going to be the congruent mod 2 relation. So we're looking at this relation, but plugging in 2. So help me think this through. Let's look at 1's equivalence class. What are all the integers congruent to 1 mod 2? Give me an example of at least one that's congruent to 1 mod 2.
1.
1 is. Okay, so 1's in there. What else is in there? What else would be congruent to 1 mod 2? If I take their difference, then it's divisible by 2.
3.
3 would be in there. What else would be in there?
5.
5. What else would be in there?
7.
All right, stop following that pattern. Pick some different ones.
17.
17 would be in there. Okay, so you see going on like that. What about any negative numbers?
Negative.
631.
Negative 631. There's one that's in there. What else is in there?
All the negative odd numbers
There we go. It's all the negative odd numbers.
and positive odd numbers.
And positive odd numbers. It's all the odds. So notice that this mod 2, this congruent mod 2 relation, kind of just divides it into the evens and the odds. And so, this would be dot, 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 all the odds. I'll just write all the odds like that, dot, 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 write them all out, all infinite many. Question, what about negative 117's equivalence class?
Still just on the
It's the exact same thing. It's just equal to that exact same class.
Why?
Because everything that's congruent to negative 117 mod 2 is going to be all the odds. Negative 117 would have showed up somewhere in here. So if two objects show up in the same equivalence class, they have to have the exact same equivalence class.
Okay. That makes sense.
Going back to the last name one. If I have the same last name as you, so you show up in my equivalence class, you have to have the same last name as me. And so I show up in your equivalence class.
Right.
So our equivalence classes would be the same equivalence classes. Okay, so there's some examples of some equivalence classes. What's the equivalence class of an element? It's all the things related to that element put together in a set. Okay, so next one. Let R be some equivalence relation on some set A, and let A and B be any two elements in big A. We're going to prove that A is related to B if and only if they have the same equivalence class.
Okay.
Right? Two objects, pick R to be, let's do a concrete one, if it's the same last name. If R has the same last name relation, then A has the same last name as B, if and only if they have the exact same equivalence class. When we did the mod 2 up here, congruent mod 2, two objects were related to each other, like 1 and negative 117, if and only if their equivalence classes are the exact same set.
Yeah.
Okay, so let's do that proof. So, this is an if and only if. We got to prove it both ways. We got to show that if the A is related to B, then the equivalence classes are the same, and then we got to go the other direction. So let's go this way first. Assume A is related to B, right? And assume A is related to B. How do I show that two sets are equal to each other?
Everything in one is in the other.
Yeah, I need to show everything that's in here is in here, and then everything that's in here is in here. So assume A is related to B, and let X be anything in A's equivalence class. My job is to now show that X must be in B's equivalence class.
Okay.
So if I know that X is in A's equivalence class, what do I instantly know?
X is related to A.
X is related to A. Because what's the equivalence class? It's a set of everything related to it. Perfect. So if X is in A's equivalence class, X is related to A. Now I already knew that A was related to B. That was given to me.
Yeah.
So if X is related to A and A is related to B, using transitivity, what do I get?
X is related to B.
X is related to B. And that's exactly what it means to be in B's equivalence class.
Okay.
Now, going the other direction, it's the exact same thinking. Let Y in B. What does that mean? Y is related to B. So then I know Y is related to B and B is related to A. How do I know this chunk?
Because
Uh-oh.
Because it's
it's
given.
symmetric.
No, I know A is related to B. How do I know B is related to A?
It's an equivalence relation, so it has to be symmetric.
Perfect. R is an equivalence relation, and so I know R is symmetric. So I know that since A is related to B, we also have B is related to A. And then once again, using transitivity, I get Y is related to A. Therefore, Y is in A's equivalence class. Therefore, the two equivalence classes are the same. So that was going the forward direction. I think I need to move my camera before I continue. All right. Moving on to the next one. So we did the forward direction. I showed that if A is related to B, then they have the same equivalence classes. Now I need to show if they have the same equivalence classes, then they must be related to each other. So now, let's assume or let A's equivalence class equal B's equivalence class. And observe that A is related to A. How do I know A is related to A?
It's reflexive.
Because it's reflexive.
Yeah.
And so, since A is related to A must be in its own equivalence class.
Yeah.
Yeah.
Shocker. But its equivalence class is the exact same thing as B's equivalence class.
Yeah.
So how do I justify going from this line to this line?
You
Because it's the same.
substitute.
The substitution on identity.
Yeah.
Using exactly the principle of extensionality, if you want to say the whole thing. But so it allows me to substitute from there to there. And so, if A is in B's equivalence class, what exactly does that mean?
It means that A is related to B.
It means A is related to B. B's equivalence class is a set of everything related to it. So A is related to B. There we go. Alright, so there's that little theorem. Not bad. Next one. Let R be an equivalence relation on A, and let little a and little b be in big A. So, setting up exactly what we had before. This time I'm going to prove that if A and B have any elements in common, if A's equivalence class intersected with B's equivalence class is not empty, they have at least one element in common,
Yeah.
then they must be equal to each other. They must have all elements in common.
No.
If I say I have my equivalence class, and I don't tell you what it is, and you have your equivalence class, and you don't tell me what yours is, but I know that Bob's in mine, and I know that Bob's in yours, then we must have the same equivalence class. Let's pick some particular relation to make that make sense. Let's pretend we're talking about the has the same height. So we have everyone that has the same height as me and everyone that has the same height as you. and Bob's in mine, and Bob's in yours,
Then everyone,
then the set of all the people that are the same height as you must be the exact same set as the set of all people that are the same height as me. That's what we're proving. So if the intersection of A's equivalence class and B's equivalence class is not empty, so there's at least one thing in there, then they must in fact be equal to each other. Good? All right. So let's get started. Assume that the intersection is not empty.
Yeah.
What does that mean if it's not empty?
They each have at least one.
There's at least one thing in there. So I know that then there must exist something, I'm going to call it C. There must exist C, such that C is in A's equivalence class, that set, and C is in B's equivalence class, that set.
Yeah.
Now if I know that C is in A's equivalence class, what do I know?
A is related to C.
A is related to C. And if I know C is in B's equivalence class, what do I know?
You know B is related.
B is related to C. Perfect. Now, just using symmetry on both these, I'm just going to say we also know the other way.
Yeah.
Good?
Yeah.
Now taking combinations of those is going to give me what I want. If I know A is related to C, and C is related to B, so look at this one and this one. Putting those two together, what do I get?
A is related to B.
A is related to B. And take this and this and put together. B is related to C and C is related to A gives me
B is related to A.
B is related to A.
That's also just symmetric, isn't it?
Or I could just apply symmetry to this if we wanted.
Okay.
Yep, both those work. So since A is related to B, then their equivalence classes are the same. How do I know that? That's what we just barely proved in the previous one. A is related to B if and only if they have the same equivalence class. So since I showed A is related to B, then their equivalence classes must be equal. So if the intersection is not empty, there's at least one element in there, that gives us that the equivalence classes must be equal. Okay, next one. Let R be an equivalence relation on A. The equivalence classes of A are non-empty, pairwise disjoint subsets whose union is A. Now this is a homework problem, but let's walk through each of these and make them at least appeal to your intuition so you feel like you can do this. So first off, what do I need to show? That an equivalence class is never empty. How would I show that equivalence class is never empty? Let this be any equivalence class. How do I know it's not empty?
It has A in it.
It has to at least have A in it. If that's an equivalence class, I must have A related to A, and so A must be in there.
Yeah.
So that's how we're going to get non-empty. How am I going to get pairwise disjoint? How do I know that two sets can never have any overlap?
You show the intersection is empty.
You can show that pick two that are different and their intersection is empty, or you can prove the contrapositive of that. Prove that if their intersection is not empty, then they're not different. And they're in fact the same. And so that part, the hard part, is actually given to you by the theorem. So the second part comes directly from the theorem. And then finally, whose union is A? How do we know that? How do I know if I union up all the equivalence classes, I get back where I started? Because every element has its own equivalence class.
Right.
And you're only selecting subsets of A. Union them all together, you get A.
Right.
So that's how that proof goes. Hopefully I gave you the logic for it, and then just writing it down, you can construct that out.
That seems pretty similar to like a basis element in topology.
Yes.
Are they related at all?
They're related in that they have that property.
Right.
Basis elements are, in some sense, the building blocks you need to construct everything. Not that it really has everything.
Right. Okay.
So when you look at everything that can be constructed from the basis elements, then you get back the entire set. Okay, so that's the hard section. The next section is real easy, and it's just partitions. What is a partition on a set? It's just dividing the set up into a bunch of non-empty subsets. So if A is a set 1, 2, 3, 4, 5, 6, a partition on A would just be dividing it into some set of subsets. So let's read the exact definition and then come down to the example. So a partition on A is a set of non-empty, pairwise disjoint sets whose union is A. We call the elements of a partition parts. So here's A, here's some set P. Notice that it's a set of subsets on A.
Yeah.
Is this a partition of A? Read that definition.
It's not empty. Oh. Fine.
Okay, so you can't have the empty set in there.
Alright.
Okay.
So when you create a partition, you can't put the empty set in there. What else do we have? Let's union all these three together. Union that set with that set with that set. What do we get?
A.
A.
A. So if you do union up all the parts, we call each one of these a part, the things in the partition. The partition is this, these are each parts. We get back A, and then they have to be pairwise disjoint. You can't show up in more than one of the parts if it's a partition. If I was going to partition up this class, I can't have Alex in one part and the other part. If I were to divide you and put half of you over there and half of you over there, Alex can't show up on both sides. So each element can only show up in one of the parts.
Right.
Make sense?
Yeah.
Yeah.
Okay. So now we create a new equivalence relation. This is the is in the same part relation. So this says A is in the same part as B.
Okay.
So once you have a partition, you can define this relation. Are two elements in the same part or not? So here's its exact definition. There exists a part in the partition such that A and B are both in that part. If this was our partition, then tell me one of the relations we could write.
One is related.
Yeah, 1 is in the same part as 2. What else could we write?
4 is in the same part as 5.
4 is in the same part as 5. 5 is in the same part as 6. We could also write 3 is in the same part as 3.
Yeah.
Good? So there's a concrete example. That's all this is saying. So now we're going to prove that it is an equivalence relation. So let P be some partition on A. Then the is in the same part relation is an equivalence relation. If we're going to prove it's an equivalence relation, what do we need to show? Reflexive, symmetric, transitive. Usually you do it in that exact order. So let's start with reflexive. How am I going to show it's reflexive? I need to pick something out of A and prove it's in the same part as itself. So let little a and big A. Now, since the union of all the parts gives me A, gives me back my original set, little a must show up in one of those parts. In other words, pick something out of here.
1.
1. Since 1 is in big A, it must show up in one of these parts.
Yeah.
Otherwise, it wasn't a partition.
Yeah.
So let little a be anything in big A. Since it's in big A, it has to show up in one of the parts. There must exist P such that little a is in that part.
Mm-hmm.
Now, if little a is in that part, then little a is in the same part as itself. Which gives me that it's reflexive.
Yeah.
Okay, so now let's prove symmetric. So now, how do you prove symmetric? You assume x is related to y and use that to prove y is related to x. So in this case, I'm going to assume or let A be related to B on our relation. Our relation is in the same part. So I'll let A be in the same part as B. If A is in the same part as B, what do I know?
Yeah, there's a.
There must exist some part in our partition such that A and B were in there.
Yeah.
So it means for them to be in the same part. Now, being a bit pedantic here, but if A and B are in the same part, you can say B and A are in the same part.
Yeah.
I'd be okay if you skipped a step like that.
Yeah.
But if B and A are in the same part, then B is in the same part as A. So I showed if A is in the same part as B, B is in the same part of A, therefore it's symmetric.
Do we just get that from set theory?
This?
Yeah.
Yeah, it doesn't matter what order you say that they're in there, because the set's not ordered.
Oh.
Okay. And then finally, transitive. I need to show that if A is in the same part as B and B is in the same part as C, then A is in the same part as C. So once again, assuming we're antecedent, let A be in the same part as B and B be in the same part as C. What does that mean? There must exist two parts. There must exist P1 for my first part, such that A and B are in P1, and P2, such that B and C are in P2. There must exist some part containing A and B, we're calling it P1, and there must exist some part P2 containing B and C. With me? Okay. Now, since B's in P1 and B's in P2, then what do I know? Then P1 is equal to P2. How do I know that?
Pairwise disjoint.
They're pairwise disjoint. No two parts have an element in common. So if I find an element that shows up in two parts, those parts must be equal. And since those parts are the same part, and A was in this one and C's in that one, then A is in the same part as C. So there's transitive. Therefore, it's an equivalence relation. Okay. Or an equivalence relation. Let's really quick use these equivalence relations to do some counting, and then we'll move on to geometry stuff. All my markers are over here. Okay, so example of where we use equivalence classes. Let's start out with one that you should know how to do really easily. Let's look at the let's look at the letters W-O-R-D. And our question is, how many words, including nonsense words, can you create with these letters? I give you the letters W-O-R-D. How many different words can you make?
Assuming there's no duplicates, right? Okay.
How many options do I have for what letter comes first?
4.
4. And we could have picked something random like R. How many options do I have for what comes next?
4.
Once I choose R there, I have 3 options for what letter could come next. So, yeah, you can't reuse the letters. I see, that's what you were asking. Can't reuse any of the letters. So it's like Scrabble. You got these 4 tiles. How many different words can you create with these 4 tiles? And so once you pick the R to go there, you only have 3 options for what could possibly come next. And then once you pick whatever you wanted there, you only have 2 options for whatever comes next. And once you pick whatever you want there, then you only have 1 option for what comes next. And there's our word that we created. Good? Okay, let's up the game just a smidgen. This time, I'm giving you the tiles W-O-R-R-D.
Okay.
You have 5 options for what comes here, right?
First.
So you have 5 for what comes first. How many for what comes second?
4.
4, then 3, then 2, then 1. The problem you have is you are going to double count if you do it that way. Call this R1, call this R our first R, and call this R our second R. If I picked W-O-R-1, R2, D, that's no different than picking W-O-R-2, R1, D. And you counted those as 2 different words, but they're the same word. Because they have the exact same letters in the exact same order. So you double counted. So how can we do this? Here's the thinking. We're going to create a partition on all the words we can create with these letters. And we're going to put 2 elements in the same partition if they spell the same word. So we would create the set of all the words we can make where we include, or a partition on where we include them if they spell the same word. So W-O-R-1, R2, D, comma, W-O-R2, R1, D. That would be in one set, since those are the 2 ways we could write the exact same word. And then continue on writing some other random combination. So O, R1, R2, W, D, comma, O, R2, R1, W, D. And we keep on going on our merry way. Now you already know how many possible ways we could arrange all these words, all these letters, if we didn't have to worry about the fact that the R's were different, right? So that was going to be 5 times 4 times 3 times 2 times 1. 5 times 4 times 3 times 2 times 1, or 120. But now, instead, we're going to count equivalence classes. How many of these equivalence classes would we have?
60.
We'd have exactly half of that, because each equivalence class contains 2 of those 120 words. And so you would end up with 60. So in this case, our answer was 60. And so the way that you did that is you did, writing it out in math, you did 5 factorial divided by 2, since that was the size of each equivalence class.
Yeah.
So that's in general how you count things like this. You partition it up by which ones are in some sense the same. You do the total count divided by the size of each partition, or the size of each equivalence class. Make sense? So let's do a more convoluted one. So there's our letters, right?
Yeah.
Now, how many letters do we have right there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 factorial ways that we can arrange those letters. But the problem is, if I swap those two S's, we didn't change anything.
Yeah.
Or if I swap those two S's, we didn't change anything.
Or the 2 I's. Which would be
Right. And so if we were to divide this up into all its equivalence classes, the big question is, how big would one equivalence class be? 10? Let's just, you can probably intuitively see that all the equivalence classes, whatever they are all going to be the same size. Right? If there's 2 different arrangements for this word, there's going to be 2 different arrangements for this word, and 2 different arrangements for each one. So we need to just pick one word and figure out how big its equivalence class is.
Right.
So let's say in this exact order, M-I-S-S-I-S-S-I-P-P-I, how many different ways could we write that out with our Scrabble tiles? So let's label them so that they're each unique. So we'll call this M, we'll call that our first I. So that's I1. This will be S1, S2, I2, S3, S4, I3, P1, P2, I4. Right? Now, if we have to make sure that once we use our letters, it comes out exactly Mississippi, how many options do I have for which letter comes first? 1. We have to start with our M. Right? Now, how many options do I have for what comes second? 4. There's 4 I's I can choose from. And that will give us our I. What about for our S here?
There's also
4.
There's also 4. Gives us our S. What about for our second S? We already used one of our S tiles. So now there's only 3 options for that S. Okay. What are we at now? I. How many options for that I? 3. S. How many options?
2.
S.
1.
I.
2.
P.
2.
P.
1.
I.
1.
So the answer is 1 times 4 times 4 times 3 times 3 times 2 times 1 times 2 times 2 times 1 times 1. That's how many different arrangements we could have made of the word Mississippi using these Scrabble tiles. Make sense?
Yeah.
Now there's a much nicer way to write this. Notice that multiplication is commutative, so we can do it in any order we want. And so notice that I had a 4 times 3 times 2 times 1 for all my S's, which is 4 factorial. I had a 4 times 3 times 2 times 1 for all my I's, which was 4 factorial. And then I had 2 P's. And then we can say times 1 factorial for M if we want. And so it turns out, just count how many of each letter there are. Write that out factorial. Your total product is how many different ways we could have written out the word Mississippi. And however many different ways we could have written out the word Mississippi is the exact same many would have been if we would have done Mississippi and put the M right there. All that does is move this M from here over to right there at the very end. And it's still just one more way that we could have done it. So it doesn't change anything. Once you find one equivalence class, all your equivalence classes are going to be the same size. So our answer now is 11 factorial, all the different ways that we can arrange the letters Mississippi, divided by the size of each equivalence class, which is 4 factorial times 4 factorial times 2 factorial. You can put the 1 factorial there if you want. So you see something like that on your homework or on your test, do not write out some humongous number. Write it out like that so I can see exactly what your thinking was. I don't care what the big number is, I care that you know how to count. Right? So there we go. Now we have this way of counting with partitions. Any questions?